I'm just recording the discussion onto the session. So I think my first takeaway is that the astronomers have discovered an amazing number of things, but for each thing they discover, there's about 4 or 5 new mysteries which are unsolved. It seems to be exponential almost. So yeah, there's a lot of stuff which the theory says should be there, which isn't there. That's a mystery. There's intermediate black holes are just not found. And how do these supermassive black holes become so supermassive in the first place? It's very difficult to explain with theory. They've got some ideas about maybe it was because of dark matter, but dark matter itself is a theory which is, the dark matter has never actually been found. They're still trying to find it. So every corner you look, there's theories to maybe explain something, but there's about 5 other problems with it. James Webb itself was supposed to give us a lot of the answers. And what has James Webb given us? A whole lot of mysteries, which don't quite fit in with the theory. So just by the way, we're hoping next year to possibly have Peter Kotzer give us a presentation about the latest findings from JWST. It might not be at a monthly meeting, it might be at one of these cosmology meetings, because he's also going to do another presentation at the monthly meeting. So that should be hopefully possibly one of the most interesting presentations we will have next year. Hopefully the astronomers will find some answers by then. Okay, go ahead.
So this is gravitational potential binding energy that you talked about. So that gets into the black hole and it emerges as magnetic energy with transitions in between.
So I mean, I think the astronomers are just flinging physics theories around, hoping they're going to hit some sort of an answer. But I think a lot of it is just speculation, really. They're trying to fit something with the observations that they have, but some of it does sort of give you an answer. It does sort of make sense. I mean, as things are coming closer, they're being ripped apart. It's creating a lot of energy, a lot of kinetic energy, which creates heat. And then there's the electrical side of things. You know, when things rip apart into electrons and protons and stuff, then you get electrical charge, then you get the formation of the electrical fields and electromagnetic fields. And all the time, things are spinning, and this creates that spinning effect. Is like, you know, like a dynamo, like an electric motor. It creates these magnetic fields, and it's happening at such a, it's close to the speed of light. It's the most powerful thing in the universe, sending out these massive rays for thousands of light years distance, never mind a couple of kilometers.
Relativity must get heavier and heavier. So, where does that energy come from? This finding is going to have
this is one of the puzzles that they. Well, this is, I mean, just the fact that so many black holes have been observed to merge. What they say, as you know, I mean, it's why the Earth isn't just crashing into the sun. If a planet, if something in orbit slows down, and it moves closer towards the thing that it's orbiting around, then it's moving a shorter distance. Therefore, that relative speed is faster, and then it comes to a balance where it's moving fast enough that it stops falling in, it stays where it is. In fact, I think I read somewhere that the Earth is moving very slowly away from the sun, at about, I don't know, 2 or 3 centimeters a year, something like that. It's not really anything significant that we can measure even in a million years, but it's happening. The only reason for that is that the Earth must be being accelerated by something like a tidal force, maybe gravitational interactions with the other planets. But the net effect is Earth is being slowly accelerated and therefore moving slightly away from the sun over the years. Same thing with the moon, of course, we know that that's a simple tidal effect, which is moving the moon away, coincidentally, also at about 2.5, 3 centimeters a year. So there are so many things. Of course, you get some black holes which are hardly spinning at all, others which are spinning. They've got indirect ways of measuring, because obviously they can't see the black hole. They can measure the effect on the space around it and fairly accurately calculate how fast each black hole is spinning and where its axis is and the angle it is and all kinds of fascinating. It's amazing what they can work out from what they do observe. So yeah.
Because imagine what could go on unobservable.
We have no evidence that the universe ends at the observable horizon.
That's right, that's fine.
In fact, its logic would tell us that it doesn't.
It's not yet a quasar. Is that?
It's, I think that it has been a quasar. That's what they said. They found that massive on above. I think they detected by radio those massive structures, thousands of light years above and below the axis. So that would have been formed by that sort of quasar-like action with the jets shooting out from the axis. I'm not sure. I think no longer. I'd have to go back through the video and yeah, that's what I. Yeah.
Everything that we've seen infinite is the terminal point for any of these things. What happens from which they die off, come to burn up, whatever happens.
Are you talking about suns, stars, star lifetimes, or? Yeah, black holes. The leading physicist theory that came to this black holes with hair theory, where black holes do slowly evaporate. Something in quantum theory or something allows it. The theory is that the gravitational attraction is so strong that within the event horizon, anything gets accelerated. Well, you can't be accelerated beyond the speed of light, but even things, speed of light is the speed limit of the universe. They're not sure exactly why that exists, but it does. It's measured. And the escape velocity, so to speak, at the event horizon is the speed of light. So apparently the Russians have the word for a black hole is actually frozen star, because an observer from a distance will see something accelerating, falling into a black hole before it reaches the event horizon. To the observer, time slows down to almost zero, so you never see it falling in. To say it's a person falling in, person would just feel itself falling in at the same speed. It's the relativity problem. Yes, that's why they say it shouldn't happen, but it does. So that's a very big unexplained thing. Yet they built those laser massive LIGO, and I don't know how many there are around the world. I think there's 4 or 5 or 6 of these structures where which have been built to detect gravitational waves. And in fact, the main chap in the US, I forget what his name is, the main scientist in charge of LIGO, came to give a lecture one year at Stellenbosch University. He's a fellow of the something institute. And I had an open lecture there and I attended it. And I asked him a question, which it took him 15 minutes to answer. all full of these postgraduates, doctors, and people sitting there were too scared to ask him a question. I arrived late and there was nowhere else to sit. I had to sit in the second row from the front. I just asked my question. Yeah. But actually, that was when he gave that lecture, they hadn't yet detected a gravitational wave. And he described and showed us a video of a whole simulation he'd done, what it would look like. And 3 or 4 years after that, when they detected it, what actually happened was exactly what he had predicted and shown in his video. So that was quite interesting. So sometimes science can be incredibly predictive and foresight, and theories can work out, and other times they just generate more mysteries than we can handle. Yeah. Anybody else? Or can we go ahead?
So we can't be destroyed. There's all the energy going into the black hole being emitted to the laser. If that's the case, is the black hole then feeding the universe with energy? Assuming you need the black hole to stay in.
So the black hole, essentially, it's an enormously energetic event, but the black hole has to be absorbing more than it's emitting. A lot more, I should think. I don't know what the theory says, what the ratio is, but it's obviously, things are falling in and being massively attracted by the gravity of the black hole. So for that to be such a powerful reaction before it hits the black hole, to be able to eject it again at those sort of the speeds of light or whatever. But of course, it's because it's focused as well in those beams. That also helps some of it to get away. But I don't know. Yes, say 1% of whatever inherent energy there is, and of course, mass is equivalent to energy. Yeah. Sorry, I just want to make one point. You mentioned that if something gets closer to the speed of light, it's a mass gets. Yeah, that's actually a myth. It's not exactly true. I've watched a video by that guy from forget the name of the place in the US Institute. But he explained it very carefully. You've got to look at the total general formula, that it's not just equal to mc squared. You've got to take momentum. That is the case for a static mass or something. That's the energy. But if things are moving, it's different. You've got to take momentum into account. So what happens is it's actually not the mass increasing, it's the momentum, the energy required to accelerate something to a faster speed. It's the sort of momentum required which is increasing. It's not really the mass. If there was a person in a rocket ship almost at light speed, and he was standing on a scale, he wouldn't weigh 1 gram more. Yeah, he actually, it's a simplification that teachers would use for school level, sort of before you looked at the full formula. It's on YouTube videos. We can send you the link. It's actually, I found it very interesting. It made a lot of sense to me once I'd watched that. It's dense. It's dense. Well, it has a tremendously strong gravitational pull because of the mass and the small volume. So, I mean, even something the mass of the Earth could form a black hole if you squeezed it small enough. And I think I saw that somewhere. What would the radius of the Earth be if it was a black hole? It would be, I don't know, maybe something like 1 centimeter or something like that. Yeah. So, then you have the conspiracy theorists saying they want to start up CERN. Oh, they're going to make miniature black holes which are going to swallow the whole Earth up. And they try to explain to them in the physics why it wouldn't happen. But until you've done it, you actually don't know. So we're still here, I think. Maybe we're not actually here. Maybe we're just an illusion. Yes. Oh, fantastic. Great. We've got a special interest group, which is called the study group, which Peter runs. Maybe he can take you on as one of the presenters next year. But basically, from now we have a meeting in January, do we?
January.
Yeah, for the monthly meeting, but yeah, and then we really start up from February onwards again. Yeah. Okay. What is your specialty? Are you an engineer? Or... Sorry, what engineer? Metallurgical. Okay. All right.
Space station.
Mm.
Myself, the first telescope that's going to be used here on your iPhone.
Mm.
So that on your iPhone you can directly read it. Whatever you need.
Mm. All right, so give your details to Peter, and it's
I'll talk to you in a moment.
I just want to check the attendees. Sorry, if any of the attendees, Ab and Robin, if you can hear me, I don't know if you've got questions. I don't know if it's going to come over. If you want to type in or comments, are you okay?
Yeah, very interesting. Listening, learning.
Great, great. Okay, we can hear you over our speakers. So if you want to ask a question, you're welcome.
Thanks.
All right. Okay, everybody else, how are we doing? Angela? Go on, aren't you going to ask us a difficult question? Okay, I hope you enjoyed yourselves, and thank you very much for your attendance. So this was a bit of an experiment to have just a cosmology meeting here besides our usual monthly meetings. Thought we'd see how it goes, and as long as we have a few interested parties and with some interesting comments to make, so I think it's worth it. So thank you very much for your attendance and your contributions. Hopefully we'll see you next time. Okay, cheers. Thanks everybody. We'll log off then. Cheers up. Cheers, Rob.